So as we transition into nuclear physics, we're going to have a lot of similar themes here as we continue through. And one of the things that we want to talk about as we get into nuclear physics and focus on what's happening in the nucleus is the going back to that experiment where Rutherford took the alpha particles and sent them, well, had the radioactive substance, and then the alpha particles went through the gold foil. And we had these very, very large deflections. And so we talked about how, if you had the plum pudding model, like in Thomson's model, the positive charges spread all over the atomic volume, you're not going to get much deflection. If you have an alpha particle that passes by, you have this large radius here. We know Coulomb's law, forces kq1, q2 over r squared. You're not going to have as much, not much deflection. But if the nucleus is really, really small, that alpha particle can get close, and then you can have these very large deflections. And that's really the only way to explain why we see those huge deflections. And so, we know that an electric field is kq over r squared. And so for a large nucleus, if we have a large nucleus, we're dealing with, a large nucleus 10 to the negative, use a different color here, 10 to the negative 10th meters. We're dealing with an electric field like this. But with a small nucleus, we're dealing with, an order of a magnitude of 10 greater with Rutherford's model. And so we have a really strong electric field that can cause a deflection, a very extreme deflection of these particles as they pass through. And again, this large-scale deflection, a strength of 10 to the 10th time stronger. So, major orders of magnitude difference there, and that allows for that huge deflection that we're talking about. And then with that deflection, we're able to actually estimate the size of the nucleus because of that extreme deflection. Okay, so let's go ahead and draw now a atomic value here for carbon. This is carbon 12, and we'll have the element name here. We have the atomic mass, protons plus neutrons up here. And then down below, we have the atomic number Z, a number of protons. So Z atomic number, and then A atomic mass. And so inside this nucleus, we have 12, 9, 10, 11, 12. 6 of those are protons, and then another 6 actually are neutrons to make a total of 12. So isotopes have the same atomic number, but different atomic mass. And so the isotopes have a similar or identical chemistry, if you have more neutrons than normal. And so, same number of protons, same number of electrons. They can have different nuclear behavior, and we're going to talk about that, especially as we get into radiation. And so a couple examples here, we have uranium-238 and uranium-235. Now, same number of protons here, they both have 92, different number of neutrons, and actually these two isotopes operate very differently, and we're going to be unpacking that and the significance of that as we get into nuclear energy. So how many protons and how many neutrons? If we have uranium-238 here, so go ahead and pause the clip and identify how many neutrons, how many protons. When you're ready to check, you can hit play to continue. Okay, so here we have, and this is a way that you can do that number of neutrons. You take the atomic number and subtract the proton number. So pretty straightforward there. 238 minus 92, we have 142 neutrons and 92 protons for our uranium-238. And then for our uranium-235, 235 minus 92, 143 neutrons. And just those 3 neutrons make a huge difference in the stability of this nucleus. And that's going to be very significant, like I said, as we move forward. Okay, so for nucleons, we're looking at, what's in the nucleus. We have protons, we have neutrons. And so with the protons and the neutrons, they exist in the nucleus. And we know the proton has a charge of positive E, just one positive E for the charge, and then the mass of 1 atomic unit. And then for the neutron, no charge, and we have no charge. The mass is 1 atomic unit, and this is how we write the symbol for a proton and neutron. For an electron and a photon, electron, again, with the charge, we know that it has a negative E, and again, E is the elementary charge. And then the mass is very small. It's considered 0. Really, it's not 0, but it's close to 0, and we have that. And then gamma, we have the Greek letter gamma there, and for a photon, no charge, no mass. And so we have zeros on the top and bottom for that. So in the nucleus, we have the 2 protons and 2 neutrons. This would be for a helium nucleus here. And we know that the 2 protons do not want to be together. We have the electrostatic repulsion between those two. We know, force equals K Q1 Q2 over R squared, Coulomb's law. And those particles want to be apart from each other. So a huge question here is, why does the nucleus not want to blow apart? And so there must be something stronger than the electrostatic repulsion, those two particles trying to get away from each other. So